electrolytic cell and electrochemical cell. Okay. So electrolytic cell, the reaction doesn't happen on its own. Okay, so for them the delta G is positive, right? Electrochemical cell actually or electrochemical reaction, the reaction can happen on its own. So delta G is gives free energy changes for the spontaneous reaction is negative for the electrochemical reactions, and for the electrolytic reactions gives free energy changes positive, right?
Yes.
Okay, so this is so here the reaction happens on its own and we get the electrical energy, we get the EMF. Okay, they have positive EMF, spontaneous reaction, they can occur on their own, they have the positive EMF, right? And we get the energy, we get the EMF, voltage of the cell. But in the electrolytic reaction, the reaction don't happen on their own, we need to put the electrical energy continuously to make them happen. So these are the two different kind of classifications. Okay, the basic classifications of electrolytic and electrochemical. So non-spontaneous reactions, okay, and anode is positive, cathode is, so this we will get into the details of the galvanic cell. Okay, galvanic cell is electrochemical cell and we use it for the generation of electric current. Okay, it is also known as voltaic cell. It is made up of two half that you already know. Okay, so this, I hope basics is clear. Okay, I guess there is no doubt in this. Anode, actually zinc has more tendency to lose electron. So zinc actually is more electropositive, it loses electrons, and that's why it is kept as anode. So anode is the electrode which is where the oxidation is happening, electrons are being released, and that's why it is negative. It is kept on the left hand side. Okay, electron flow from anode to cathode, and this is the overall cell reaction. Overall cell reaction, uh, you can note down the zinc is getting oxidized, the copper is getting reduced. Okay, and this is the cell representation. You should be clear with the representation. Any doubts in this?
No.
Okay, so this is the basic thing. Yeah, in case of any doubt, do ask me, right? So, and this is the cell representation. Clear? So you will represent the cell by writing the anode on the left hand side, cathode on the right hand side. Zinc is changing to zinc sulfate. This, what this vertical line represent? This represent two different phases. Okay, zinc is solid and the zinc sulfate is in aqueous medium, so you are going to put the vertical line. And similarly, this is the salt bridge. You are having copper solution. Copper solution is taking electrons and changing to copper and going and getting deposited on the copper rod, right? So that is going to be the cathode. Okay, this is the normal representation of the galvanic cell. You also put the concentrations, okay, along with the state, that can also be put. So this already, I hope it is clear. Salt bridge purpose, there are some questions related to the purpose of the salt bridge. Okay, what is the use of the salt bridge? It maintains the overall electrical neutrality of the cell. It completes the circuit of the cell, and it prevents the accumulation of charges in the different cells, which may lead to stoppage of current. Okay, So this is the thing which you should know, right? Basic thing.
Yes.
And one more thing, that the cation and anion which you need to take in the salt base should have same mobility. Suppose if you take potassium nitrate, okay, so NO3 minus, in this case the zinc is getting deposited here. So NO3 minus will come in this compartment, okay, and the potassium ions will go in that compartment. So they need to have same ionic mobility, so that they can flow easily on both the in both the compartment and can neutralize both the compartment very easily. Okay, so this is how we need to uh, calculate. Okay, we need to know some basic questions can come up, right? So that you should know. The other thing is your EMF of a cell. EMF of a cell is the total voltage of the cell, and for that you need to calculate the individual electrode potential. So how you are going to calculate the individual electrode potential? So what's the method to calculate the individual electrode potential? Can you tell me quickly? How do you measure the electrode potential of individual electrode? Yeah. So you connect each electrode with standard hydrogen electrode, right? Standard hydrogen electrode is taken as a reference electrode whose electrode potential is taken as 0. Okay. And you connect each one of them with the standard hydrogen electrode and you calculate the EMF. Okay. You calculate the electrode potential and you calculate the EMF of the whole cell. Right? Electrode potential. This is clear. Any doubts in this? Then we can start some of the questions.
No, sir.
Okay. So, yeah. So this is the standard hydrogen electrode, in which the hydrogen is bubbled at standard condition. Platinum wire is taken, and 1 molar HCl is taken. Okay, 1 molar HCl will help. It is only under standard conditions, so you can look over here. The hydrogen H plus can from the HCl can accept electron and change to hydrogen gas, and or vice versa. Hydrogen gas can come in and lose electron and change to H plus, right?
Yes.
So this is only in the standard condition, and its electrode potential is assumed to be 0. Actually, you don't know what is the electrode potential, because until unless you can't measure the absolute value. Okay, so what we do, we take this as a standard electrode potential and we connect each one of them, each other electrode with it, okay, to get the value. So this is considered as 0 volt. And when you connect any other electrode, you make a cell out of it, complete cell, cathode, anode, you measure the voltage, and this is 0, so you know what will be the electrode potential of the other one, right? So these are the standard conditions. Okay, yeah, so let's do this. So reduction potential of any half cell is measured against what? And what's going to be the answer? Yeah, Memuna. Any half cell? Yeah.
Copper.
Which one?
Option C.
Option C. No, it's the standard reduction potential of any half cell. Half cell means only copper or only zinc if you are taking. Suppose if I take a single electrode, and we know that the single electrode will not work on its own. Okay, it is measured, it is dipped in zinc sulfate solution. It will not work, that we know, 1 molar zinc sulfate solution. Now the question is, how to measure its electrode potential? First of all, it is very difficult to measure because it is alone. So if it is alone, it is not going to work, right? The current will not flow. And if the current will not flow, the question is how you are going to measure its electrode potential, right? That's the problem. Okay. So and when, so you need to connect it with someone else. Okay. But if you connect it with someone else, the problem again is that other one will have its own electrode potential values, and that will affect its own electrode potential values. So what you do, you take a reference electrode, and that is standard hydrogen electrode. Just now we have seen. Okay, so this is a cylindrical jar which is used to, and this is the platinum foil, and this is sealed platinum wire so that it doesn't get spoiled in the HCl, and you bubble hydrogen gas at 1 bar. This is standard hydrogen electrode. Okay, clear?
Okay.
So this is 0 volt. You assume it to be 0 volt and you connect it. So whatever the voltage you get, okay, so that will be, because this is 0, we have assumed it to be 0, so it will be taken for the zinc. Okay, so that's how it is measured. So standard hydrogen electrode is used to measure. So standard hydrogen electrode is the platinum electrode in which the hydrogen gas is bubbled and in the H plus solution with 1 molar concentration. And if the temperature is also given, that is 298.25 degrees Celsius, 298 Kelvin. Okay, these are the standard conditions. And pressure is 1 bar. The hydrogen gas is put into the electrode at 1 bar. So these are the standard conditions. And we assume this to be 0 volt, so that we can measure all the rest of the electrodes. Okay, with respect to this. So this is the hydrogen half cell. It is nothing but the standard hydrogen electrode. The hydrogen half cell is this also, but this is not going to be the answer. Why? Why do you think that this is not going to be the answer? It is because these are not the standard condition. Okay, this is 10 to the power minus 7 moles, right? Is it clear? So you need to take the standard condition. Okay, so this is again the diagram how it shows how it is measured. Suppose if you want to measure the electrode potential of copper experimentally, you will connect the copper with the standard, this is standard hydrogen electrode, and look at the pressure, look at the concentration, they are at the standard condition, and the temperature also is 298 Kelvin, that means 25 degrees Celsius. Okay, so and this is the copper also should be taken 1 molar, 298 Kelvin. This is the anode. Okay, this is the cathode. Okay, and you make a overall cell reaction out of it. You get the EMF of the cell is E cathode minus E anode in terms of reduction potentials. And you measure experimentally, it is 0.34, this cathode minus anode, and this you assume to be 0. So that's how you calculate, estimate the actual electrode potential, and this will be given to you. But question can come if it is asked that what are the standard condition, what is standard hydrogen electrode. So this question is Same only. This is not the standard hydrogen electrode because the concentration is not 1 molar. If the temperature also is not 298 or the pressure also is not 1 bar, then it is not the standard condition. So you need to take the standard condition, then only it will be considered as standard hydrogen electrode. So I hope you understood this. Okay, this is how it is measured. You put a voltmeter and that let you measure the electrode potential of copper, because this you have taken 0. Clear? So now you have electrodes, different electrode, each one of them being measured by standard hydrogen electrode, and you have the values of all the electrode potentials. So electrode potential, you know that can be standard reduction potential or standard oxidation potential. But if nothing is mentioned, it is written over here as per IUPAC convention. The reduction potential is taken as the standard electrode potential, which is a measure of electron accepting tendencies. Okay, though we can measure this also, it will just be the opposite. The sign will be plus, this will be minus, but this is taken as the standard reduction potential. Okay, and how this is measured under standard condition mean there is a not standard condition. It is measured by connecting the zinc electrode to the standard hydrogen electrode. Okay, and we make us so all these electrode potentials, you know, are arranged, and we make a electrochemical series. Okay, so tell me which is the best reducing agent. Yeah, who is the best reducing agent? These are reduction potential values, and these are the questions which are most common questions asked for the electrochemical series or the standard electrode potential, the application of this electrochemical series. This electrochemical series actually is prepared by connecting each half electrode. These are the half reactions. So you connect each one of them by the standard hydrogen electrode, and from that you measure what is going to be the value of each one of them, right? And this whole series which you get is known as electrochemical series. Okay, so electrochemical series, there are many elements. You should know that the lithium is the best reducing agent. Is it clear why it is the best reducing agent? So it's not accepting electrons, minus 3.04 volt. Okay, what it means? It means the lithium plus ion doesn't want to accept electron. That's why its electrode potential is so negative. Clear? So if you put the equation in a reverse manner, it will look like this: lithium giving lithium plus an electron. And because you have reversed the equation, the electrode potential will also change its sign. So 3.04 volt means it is losing electrons. Okay. So for gain, it is very negative, mean that lithium plus doesn't want to gain. But when you want to, when it is reversed, you can make out that the lithium can give its electron. So lithium is the best reducing agent. Okay, this one is going to be the best reducing agent. And who is the best oxidizing agent? Tell me. Yeah, which one?
The lead.
Yeah, F2 fluorine is the best oxidizing agent. It is the one which can accept electron most easily. So it is highest, the one who is having highest oxidation, highest accepting tendencies will be the best oxidizing agent. Clear? So mostly your first questions which you are going to face is related to this electrochemical series and its application, right? Any doubts in this?
Yes.
I am assuming that you have studied but if you want to know anything, just stop me and tell me, I will explain, no problem. So actually the hydrogen is taken as 0. So if it is above hydrogen, that is positive value. You can see this is hydrogen. And that species has more tendency to accept electron. And they are good electron acceptors. And the elements which are below hydrogen will have negative standard reduction potential values. Means they don't want to accept electrons, or their electron accepting tendencies is low. And if their electron accepting tendencies is less, what it means? It means that their neutral element can lose electrons more easily. Suppose if the chromium has less electron accepting tendencies, chromium 3 plus means it will have negative SRP value. If you do the reverse, the chromium will have positive oxidation potential, means it can lose electron most easily. So chromium is going to be a good reducing agent. Okay, so most famous questions are related to this, right? So let's do this. These are asked in every examination. Yeah,
Zinc.
yeah, strongest reducing agent. Yeah, so the one who is not accepting is this one, because it is having very negative value. Largest negative value means the zinc plus 2 doesn't want to accept electron. And if you do the reverse, zinc will lose electron very easily, right? So I hope this is clear. Okay. What about this one? Yeah, iron accepting 2 electrons, minus 0. Zinc accepting 2 electrons, minus 0.7. So who is more electropositive? It's the iron or it's the zinc?
The iron.
Which option?
B.
The Fe is more electropositive. Fe, suppose if electropositive metals are electropositive because they have tendency to lose electron. Okay, and this is electron accepting tendencies which is shown over here. And if you want to show the electron releasing tendency, you can just reverse it. But don't forget to reverse the value. Okay, this is going to have plus 0.44 value. Okay, hold. And for this one, it is going to be zinc giving electron, zinc 2 plus 2 electron. This is plus 0.76. So if the EMF value or if the electrode potential is If it is positive, means it can happen very easily. Okay, and higher the positive value means more easily it can happen. And because we want to measure the electropositive character, means the one who can lose electrons most easily, and that is zinc. So zinc is more electropositive than iron. Clear? Is it clear?
Yes.
Right? So just you can compare. So basic questions will come, right? And so let me take some questions, some more, or we can do that. This is the electron accepting tendency of oxygen. Okay. And there are some other electron accepting tendencies given to you. So who is the strongest oxidizing agent? Yeah.
Option 3.
Option 3. Yeah. So it is accepting. So check whether it is accepting or donating. Okay, this is accepting electrons. Okay. And it is having the highest value out of all. So this is going to be the strongest oxidizing agent, right? So there are many questions related to this. Most common application. The another application is you can calculate the EMF of the cell. Okay, you measured only half electrode potential that you can, and that too under standard condition. Okay, under standard condition you can measure it, right? And by connecting it to standard hydrogen electrode. But that was the electrode potential of only one electrode. What is going to happen if you make a, for making a cell, you need to connect the two electrodes. So what is going to be the EMF of the cell? You need to take the difference of the electrode potential. So what you do, though we can measure in any way, but what you do, you take the standard reduction potential of cathode minus standard reduction potential of the anode. Okay, but this is only in the standard condition. So I'm going to put E naught cell. E naught cell equal to E naught cathode minus E naught anode. Right, that's you are going to do. But this is both in reduction potentials. If you are taking reduction potentials, you are going to take the electrode potential where the reduction is happening minus the electrode potential. Both should be in reduction potentials. Okay. So you are going to take the electrode, first electrode where the reduction is happening, minus the electrode potential of the electrode where oxidation is happening, right? But if you are going to take the oxidation potential, you can measure, you need to take the difference, because this is IUPAC convention. So that's why we can use both. We can write the reduction potential for both of them and take the difference, right? If it is oxidation potential, you need to take the electrode potential where the oxidation is happening first. So E naught anode minus E naught cathode. Okay. This is also the formula, and each one will be the value will be given, and that value was found out using standard hydrogen electrode. So you need to take the difference. If they are reduction potential, so you need to take the electrode first where the reduction is happening minus the electrode where the oxidation is happening. But if you are taking oxidation potential, then you need to write the oxidation potential first minus the reduction, the oxidation potential of the electrode where reduction is happening. Or there is one more formula you can write where you can write the reduction potential plus oxidation potential, reduction potential of cathode, and oxidation potential of anode. So all the formulas same, but what I would like to suggest is stick on to this formula, calculate only with respect to the reduction potential. Okay, because this is the standard reduction potential which is given by IUPAC. Okay, so this is going to be more easy. Okay, suppose if you are using the more and more methods, it can become very difficult, or it may sometimes you may go wrong also. Okay, right. So we can find the electrode potential, and the other thing is what to do with the electrode potential, but that is only under standard condition when the concentration is 1 molar, temperature is 298, 1 bar pressure. But if you have changed the temperature, if you change the concentration, then the electrode potential is not going to be the standard. So how to calculate that? We use Nernst equation for that. Okay, as of now we can calculate directly. Okay, using the electrode potential, and the electrode potential is standard electrode potential. Take the difference, and the EMF of the cell comes out to be positive, then the cell reaction is going to be feasible, it is going to work, cell is going to work. But the EMF of the cell is comes out to be negative, then the cell is not going to work. Okay, that you need to know. Yeah. So do this question. So for 10 it is given, for chromium is given, both are reduction potentials. Okay, and when they are connected to one another to make a cell, what's going to be the value of this voltage of the cell?
Option B.
Option D. You want suppose if you are given with 2 electrode and you are asked to make a cell, you are going to put the electrode which is having higher reduction potential at the cathode. So who is going to become the cathode? This one is going to become the cathode, right? This one is higher value plus 0.15 minus minus 0.74. Okay, so what you are going to get? It's option A, right? What mistake you did? You need to take care of the sign also.
Yes.
So minus minus plus plus 0.74. So 9.89. And this is only under standard condition. Okay, so you need to decide on your own which is cathode, which is anode. And the one which is having more reduction tendency, you are going to make it as cathode. Just look at them very carefully, because in the examination what may happen, they may not give you in the both reduction potential. They may give some reduction potential and oxidation potential for some of them. So you need to convert all of them to reduction potential, and in order to make a cell out of it, you need to take the higher reduction potential minus lower, minus along with the sign you need to take, so that is plus. Okay, yeah. So this is also a cell. So what's going to be the standard electrode potential for the cell reaction, which is given below? Yeah. So which one is cathode, which one is anode? First, you need to determine that. Both should be in reduction potential. Then cathode minus anode. So this is accepting Mn2 plus is accepting electron and changing to Mn. This is having minus value. So 0, this is minus 1.18 volt. Okay. For equation number 1, right? And the one who is accepting is Mn3 plus. So all are manganese. So it may create confusion, but they are not same type of manganese. Okay, some are Mn plus 2. So if Mn plus 3 is there and Mn plus 3 accepts an electron, that's going to have plus 1.51 volt, plus 1.51, right? This is larger than 0. Is it clear?
Yes.
So this is going to be the cathode, and this is going to be the anode, right? So right, so there are two different things. Now listen very carefully. So suppose if it is asked to make, if it is asked uh, from you that you need to make the cell, then you will make this as a cathode and this as an anode. Okay, if it is asked from you, make a cell out of it. Okay, but these are two different questions. Listen very carefully. This is where everybody can make mistake. If it has asked you to make the cell, you will take the cathode minus anode. Okay, but if the cell reaction is given, if the cell reaction is given, then the cathode and anode are already given to you. Okay, then you will not decide who is cathode, who is anode. So from the reaction only, you need to identify who is cathode, who is anode. So Mn plus 2 is taken. Mn plus 2 is changing to Mn, right? This one. This Mn plus 2 take 1. This is changing to Mn. So this is getting reduced. So this is cathode. In the equation, this has taken as cathode. And Mn3 plus Mn2 plus changing to Mn3 plus. Mn3 plus is given on the right hand side. So Mn3 plus, this one is not accepting electron, but this is Mn2 plus is losing electron because Mn3 plus is written on the right hand side. So it is going to be like this: Mn2 plus and Mn3 plus electron. So this is going to be the anode. So I will look at the species which are given. Cathode is going to be the upper equation. Okay, and the anode is given in the lower equation. Suppose if it is not, the equation is not given, if it is asked from me to make cathode and anode, I will make the higher reduction potential as cathode, lower reduction potential as anode. But in this question, they have given you the cell equation and they are asking you what is the electrode potential of this cell equation. They have given cathode and anode directly. So you are going to take the cathode and anode which are given in the equation. Okay. So this is cathode, this is E cathode minus E anode. So minus 1.18 volt minus 1.5. Is it clear, Emuna?
Yes.
Okay. So just look at this. So overall, it's going to become negative. Right? So will this reaction happen? Is it a spontaneous reaction? Is it going to happen? Have you understood? If the equation is given, you will work as per equation. But if the equation is not given, then you will, on your own, you will take the higher SRP as cathode. Right?
Yes.
So the cell reaction is non-spontaneous because you are getting the negative SRP values. Okay. Let's do this. So in this case, the equation is already given. You are going to consider the cathode and anode as per the equation, not as per your own choice. Okay. Actually, most of the students get confused in this case only. They themselves decide that they actually get confused when to decide on their own whether who is cathode, who is anode. So if the equation is not given, then you will decide on your own. But if the equation is given, then you do the work as per the equation, right? So what's going to be the answer? So who is cathode? Tell me. Who is getting reduced? Yeah. Iron. Sn is getting reduced. You have seen, you have taken these values. Okay. So 0 and minus 0.14 minus, so these are minus values are lower, 0.14 4. This is lower. So 10 is higher. So you take the higher SRP means reduction means cathode. So you are telling as per this. But what I told you, if the cell reaction is already given, then you will not decide on your own. Then you will decide as per equation. Is it clear?
Yes.
So who is the anode, who is the cathode? Tell me who is the cathode in this, as per this equation. As per the values, you are correct. You are correct. But because the equation is given, we need to work as per the equation. So who is the cathode?
F.
Fe. Fe is taking the electrons. Okay, so Fe is the cathode. Cathode is Fe as per the equation. And 10 is anode. So you are going to take the reduction potential of the cathode. Reduction potential of the cathode is minus 0.44. Okay, minus reduction potential of the anode. Reduction potential, this is anode. Look here, it is losing electron. Okay, as per the equation, I'm going to work. So minus reduction potential of anode, that is going to be this one. So overall, it is going to be minus 0.3 volt. Okay.
Yes.
So the cell is not going to work actually, right? So other applications are, so I hope this is clear. Actually, if the values are given, you will yourself take the cathode and anode, so that your decision was correct. But if the equation is given, look at the equation very carefully and check who is the cathode, who is the anode.
Yes.
What the other application of electrochemical cities is, suppose if you put a metal in acid, some metals liberate hydrogen gas. Other metal do not liberate hydrogen gas. Okay. So how you are going to decide? So you have some standard hydrogen electrode, that is an electrode or it is also a reaction. Okay, both. So this is reaction as 0 volt. There are some reactions which are positive. SRP values means, and the positive one are the one who want to accept electron more desperately. Okay, they want to accept the electrons more, in more amount, larger. They have a larger tendency. That's why they have a high positive value. So definitely, suppose F2 is going to have a high positive value, highest, that is the strongest oxidizer. And you can't expect these elements to give their electron because they have more tendency to accept electrons, so they will not give their electrons. So, but if you move down the electrochemicals, they will have negative values, right? Negative SRP values. Okay. For example, if you take iron, Fe2 plus 2 electron, Fe means Fe2 plus doesn't want to accept electron, or Fe can give electron very easily from Fe2 plus, both. So it means what? It means they will not lose, they will not gain electron, mean they can lose, so they can reduce hydrogen. Okay, so the ions which are actually the species or the electrodes which are in the lower region, okay, they are actually good reducing agent and they can give their electron more easily. Clear? So this you need to consider. Okay. And the other thing is Nernst equation. So when do you use Nernst equation? Tell me. Any idea? Yeah, Memuna?
Mm,
And Nernst equation, suppose if you are asked to measure the electrode potential under standard condition, you just take a difference, okay, and calculate. But if it is non-standard condition, means the temperature and pressure are changing, the concentration is not 1 molar, then it is non-standard. Okay, so for that you use Nernst equation. Nernst equation will help you to calculate the electrode potential under non-standard condition, right? So how we are going to do that? We will look at it. So let's discuss more about the electrochemical series. Just one more question. This one. So which of the following statement is correct? Yeah. So 10 is minus 0.1 minus 0.14 and the copper is plus 0.34. Both are reduction potentials, right? Yeah, tell me what's going to be the answer.
Option C.
Option C, tin ion can be reduced by H2. So H2 is so reduction potential. Okay, you can write it like this. So this is 0 volt. Okay, and 10 plus 2 taking 2 electrons and changing to 10. This is minus 0.14 volt. This is lower, minus is lower, and the copper is higher. Okay, copper accepting 2 electrons, that is Cu, that is plus 0.3. Because it is plus, it is placed at above hydrogen. Now you have told me option C. So 10 plus 2 ion can be reduced by hydrogen. So who is having more tendency to gain electrons? So can hydrogen give electrons to 10? Are the 10 having more tendency to accept electrons as compared to hydrogen, or is the hydrogen having more tendency to accept electrons? Yeah, tell me. As per the equation, you can write it in this way. Okay, you will never go wrong, right? So tell me, who is having higher tendency to accept electrons?
Cu.
Is it the H plus or 10? Accept electrons. H plus is having higher tendency because it is having zero value, which is larger than the minus 0.14. Minus 0.14 is lower. Okay.
Yes.
Okay. So H plus is having more tendency. So H plus is more a tendency to accept electrons. So H plus will take the electron and they will not give it to 10. So 10 ions can be reduced by H plus? No. Can tin ions be given electron by the H plus ions? No, because H plus ions have more tendency to take electrons. Clear?
Yes.
Okay, so this is not correct. So copper can be oxidized by H plus. Copper can be oxidized by H plus. It can happen only if the hydro H plus can take away the electron from copper. This cannot happen because the copper is placed higher, so copper is more desperate to take electrons. So H plus can't oxidize copper because copper has more tendency to accept electrons. This is also incorrect. Copper ion can be reduced by hydrogen. So hydrogen gas and the copper ions you have taken. So who has more tendency to accept electrons? It is the copper ions. Has more tendency. So copper ions can be reduced by hydrogen gas. Yeah. Copper ions will accept electrons more desperately than H plus ions. So what is going to happen? The copper is going to take the electron from the H2 to make convert it to H plus. Okay, so the above reaction can happen easily. So this is correct. Copper ions can be reduced. Okay, copper ion can be oxidized by tin. Means copper ion, the tin can oxidize uh, copper. Oxidation means loss. Can Sn2 plus bring in the loss of electrons from copper? No. Okay, because tin itself doesn't want to electron. It doesn't want to accept electron. How can it take electron from the copper? Copper is more desperate to take electron. So tin can't oxidize. So this is also incorrect. So option A is correct. Clear? Right?
Yes.
So you need to think in this way, and you will get your answer. Okay, just uh, or we can do some more questions, little bit, and just you can practice, but you need to think in this way. Let me put one more. And these are the common question in NEET JEE everywhere. And everybody make mistake in hurry. Actually, everybody know, but actually in hurry, everybody can go wrong. So this is the question, and they are asking, what is the oxidizing power? Okay. Yeah.
Option 2.
Option
2.
option 2, you are telling. So oxidizing power, these are the reducing powers. Okay, because they are shown to gain accept electrons. Okay, so this is the increasing reducing power. Increasing, sorry, not reducing power, oxidizing power. Because they're themselves getting reduced, this is the reduction potential, they can accept electron, they're themselves getting reduced, but from where the electron is going to come, it is going to come from other substance. Okay, is it clear? This is the reduction potential, SRP, electron accepting tendency, and this is the strongest electron acceptor. And if it is the strongest electron acceptor, it can take electrons from other substances very easily. Because it is most desperate to take electrons, copper, cobalt plus 3. Do you agree with this? Cobalt plus 3 has highest tendency to accept electron. So it can take away the electrons from any other substance. Okay. So it can bring in the oxidation. It can make some other substance to lose electrons. Why? Because it itself want to gain electron. So it can bring in the oxidation of any other substance most readily, because it itself has highest tendency to accept electrons. Is it clear? So cobalt 3 plus is going to be the strongest oxidizing agent. Clear? Getting it?
Yes.
Don't worry if it goes wrong. Okay, initially, actually, all the students, okay, daily, a lot of students study this topic, and initially it happens. Okay, don't worry about that. Just little bit practice. With practice, you can do it correctly. Okay, so oxidizing power, okay, means the power to make someone loses electron. So when the oxidizing power is going to increase, which ion is going to have highest oxidizing power? It is the ion which itself want to accept electrons most desperately, that can cause the oxidation of other substances. Okay, right? So cobalt plus is the strongest oxidizing agent, followed by lead plus 4, followed by cerium, and then the bismuth. I hope this is clear, right? Yeah, Memuna, any doubt in
No, sir.
this? Okay, right. And this is the Nernst equation. Okay, so suppose if you have this equation, and if you want to calculate the EMF of the cell or electrode, this is applicable on both. On the cell, or a cell is complete cathode, and single side is known as your electrode. So it can be applied for both. It can be applied for the electrode as well as for the cell. So E cell, which is the non-standard, the not is not there, equal to standard EMF minus R is the gas constant, temperature in Kelvin, by NF. N is the number of electrons which are transferred from cathode and anode. F is what? F is Faraday's constant. Okay. This is the charge of the electron for one. This is the charge of 1 mole of electrons. Okay. And this is the reaction quotient. In 11th class, you must have studied equilibrium. So this is the reaction quotient. So reaction quotient, it's look very much like the equilibrium constant. So concentration of C raised to the power, the coefficient concentration of D raised to the power, the coefficient of the balanced equation divided by concentration of reactant, each raised to the power their uh, stoichiometric coefficient. Okay. So if you have actually uh, if you take the equilibrium concentration, that becomes equilibrium constant. But if you take any other concentration which is not equilibrium, then it becomes the reaction quotient. Okay. So whatever the concentrations are not given, and if they are all 1 molar, this is log 1 is 0. Okay, so then you got, if every concentration is 1 molar, you are going to get the value of as E naught, because this whole term is going to become 0. Okay, so this is how, this is the Nernst equation. It is these are all constant at 298 Kelvin, so their value is taken as 0.0591. Okay, so you are also studying CBSE at the Learnivio, or only for the JEE?
Both.
For both. Okay, yeah, okay, no problem. So just this is another example. Okay, this one I have given zinc, and this is concentration is C1, copper concentration C2. Okay, this is the anode, this is the cathode. Okay, this is the cell equation. Cell equation you need to write. That is very important, because and you need to multiply to get the proper electron balanced on both the sides. Otherwise, if you don't balance the electron, the equation is going to go wrong. And if the equation is going to go wrong, then whole of this value is going to go wrong. Okay, so this same value are, so E naught cell you can calculate from the E naught. Take the difference of cathode minus anode minus plus, so it is going to be 1.1 volt minus RT by NF. Change it to this natural logarithm to log to the base 10. This is 0.0591 by n is going to be, so you don't take the concentration of solids, because the concentration of solid don't change, it remains same. Okay, so you take the concentration of zinc and copper, right? And n is going to be 2, because you have 2 electrons are transferred, right? And whatever the concentrations are given, according to that you can calculate the EMF of the cell. So let's do this question. This is just the basic one. Yeah, tell me. This is direct question. What's going to be the answer? Yeah, the EMF of the galvanic cell is negative. This implies that infer. EMF, overall EMF comes out to be negative. The cell reaction is non-spontaneous, means it will not happen. Is it clear? Okay, this is the direct question, right? And positive EMF means cell reaction can happen. Okay, so this we can cover on the next time. Meantime,